Hello, everyone, and welcome to this session that will introduce you to the basics of Martian geology so that if you're assigned a mapping project in a mapping class, you'll have an understanding of what some of the rocks of Mars are and how we know that. So what sorts of data sets do we have currently available from Mars to use in this exercise? Mars is a great place to go to find conditions that are surprisingly Earth-like if you want to do geologic mapping and similar activities. Many of the geologic processes we see on Earth are active and present on Mars. There's erosion, there's wind, there has been flowing water, there has been chemical weathering, so we see sedimentary rocks, we see layered rocks, and conveniently, we have an enormous amount of data from certain areas on the planet Mars, including remote sensing images from orbit, samples that have been analyzed at the surface by rovers, and actually some meteorites that are available that give us mineralogical and chemical constraints on the whole planet. So Mars is a place where we can learn to do some geology. Let's cover some of the basics of Mars, followed by how we know that, and then give an introduction to the sites on Mars where the rovers sit. To first order, Mars is a basaltic world. Mars's crust is basaltic. There are many, many basaltic lava flows. There are very large volcanoes. There are a handful of more felsic sites and a good number of alkali basalt spots, but overall, the composition of Mars starts off as basaltic rocks. There are very large volcanoes. In fact, the largest mountain in the solar system is a volcano on the surface of Mars, and there is a large canyon or rift system that is associated with the growth of this large volcanic province. Today, Mars's surface is dry, mostly below the freezing temperature of water, and basically desiccated. Mars is effectively a dry, frozen desert today. The processes that are active on Mars are processes we think of in a cold desert on Earth. There are sand dunes, dust devils, wind. Although the atmosphere is thin, dust and wind are able to blow there. There are CO2 and H2O ices and very little, if any, water present on the surface. And Mars's surface is covered by impact craters that have been formed over the last 4.5 billion years. In the past, however, Mars was a far more active world. At times in Mars's history, there have been large amounts of water, liquid water, present on the surface, enough to carve channels, enough to move sediment, enough to pond, maybe in large areas of the planet, including water that was mostly fresh water, at least not extremely salty. So Mars has had substantial amounts of water flowing across its surface. This was not, unlike Earth, enough to rework the whole planet, so that Mars does preserve many features that formed very early in its history, but it is enough water to leave a very strong imprint on the chemistry and mineralogy of rocks and on the sedimentary processes of Mars. Finally, on this page, one of the important features of Mars is a northern-southern hemisphere dichotomy, meaning there are two types of crust on Mars. The northern hemisphere of Mars is lowlands with much younger and much flatter terrain. The southern hemisphere of Mars, on the other hand, is older and much more heavily cratered highlands, which you'll see on the data on the next slide, which I'll use to start introducing our data sets with the image from MOLA, the Mars Orbiter Laser Altimeter. This was a fascinating instrument that flew around Mars, fired laser pulses at the surface, and detected the travel time. And since Mars, unlike Earth, has no vegetation on its surface, this instrument was able to give us an extremely accurate image of the topography of Mars in many areas. You can see that Mars has high mountains in a volcanic province. You can see that the southern hemisphere of Mars is highlands. at higher elevation that are highly cratered. The northern hemisphere does have some craters, but it is lowlands, and there is a boundary somewhere in the middle that we call the dichotomy boundary, representing the shift between lowlands in the northern hemisphere and highlands in the southern hemisphere. We also have a variety of image data sets collected from orbiting spacecraft. Just as an example, this is not exhaustive. Some of the best images of Mars's surface have been captured by a spacecraft called the Mars Reconnaissance Orbiter that has been orbiting Mars for more than a decade now. It carries 2 cameras on it that image Mars at different resolutions. The CTX, or context camera, images Mars at a maximum of 6 meters per pixel, meaning that it can see potentially a large boulder or small outcrops. And this takes a broad image as a stroke over Mars, like you see in the frame at the right. And in the time that this spacecraft has orbited Mars, CTX has created a nearly complete global mosaic covering most of the surface at this resolution. That spacecraft also carries a much higher resolution imager, the HiRISE image, which is a great camera. It can zoom in to the point where it can see 25 centimeters per pixel, giving you a view potentially of 1 pixel of a rock this size. At the lower left of this frame, there is a HiRISE image where you can actually see the Curiosity rover zoomed in on, captured by part of HiRISE. That same spacecraft also has one of several spectrometers that have orbited Mars. This is the most recent, and it is the highest resolution. PRISM, the Compact Reconnaissance Imaging Spectrometer for Mars, doesn't have the same resolution as HiRISE, but it takes images at 544 different wavelengths. And by looking at the absorbance of the surface in various wavelengths, you can recognize the signatures of specific minerals. So PRISM can give you a true color image of Mars as seen at the left, infrared images of Mars as seen in the next image, or you can pull out specific wavelengths, put those wavelengths into a place where your eye can view them, even if they're in the infrared, and that can allow you to see the locations of minerals that absorb at certain wavelengths. For example, here you can see outcrops of iron-rich clay and of aluminum-rich clay, both of which are important to find on Mars because clay minerals are indicative of high water contents and erosion and weathering of the surrounding rock material. Finally, we head down to the surface with our rovers. Now, for this talk, I'm going to focus on the Curiosity rover, which was the small car-sized rover seen at the right of this image. There are several other rovers that have visited other sites on the surface, but for this exercise, we're going to go to Gale Crater. So let's meet the Curiosity rover behemoth. Some, not all, of its instruments are particularly useful for understanding what we might go after in this exercise. MOLLE, the Mars Hand Lens Imager, is literally like a rover that has a hand lens on it. It can zoom in on rocks so that you can see the texture just like you might see out in the field using your eyes. The ChemCam instrument is a laser-induced breakdown spectrometer, or LIBS, meaning this is the laser. It literally fires a laser at rock, causing some of that rock to vaporize so that it can measure the spectra given off of that, determining the composition of the laser shot. And this can be used to probe what minerals you're targeting. The elements that are given off by a plagioclase, a feldspar, will be different from those given off by a pyroxene, and you can use this LIBS instrument to tell what minerals you've shot. The APXS, the alpha particle X-ray spectrometer, is able to give you bulk chemistry of a target. This is like doing an X-ray fluorescence analysis of a powdered sample on Earth, so you can tell the difference between a basalt and an andesite, or a basalt and a dacite, things like that. And finally, for this list, again, not exhaustive for all the equipment on the rover, The rover carries an X-ray diffraction instrument called ChemIn that can be used to determine the mineralogy of the rocks that it analyzes. That rover landed a few years ago at a site called Gale Crater, pictured here. Gale is located near the Martian equator on the dichotomy boundary. As you can see on the right, the crater is a large crater with a moat in it and a central mound that is kind of a mountain called Aeolus Mons, or Mount Sharp, named after famous mapping geologist Bob Sharp. There is sedimentary layering that is visible from orbit on the central peak. And that layering and some analyses from the CRISM instrument that showed you can find rocks there with high concentrations of clay minerals are some of the reasons why this site was chosen as the target for this rover mission, because clay minerals are expected to form when there are large amounts of water present over a long time. This video, assuming it plays correctly, will zoom in gradually on the location of Gale Crater, and now you can see we zoom in gradually to where the rover landed in this crater relative to that central mound. So we're off to the northwest of that central mound and near Mars's equator at the spot where this rover landed. When the rover landed, it saw some of these rocks. Many of them you will find looking very familiar based on what we know from Earth. Here, in the image at the left, is a conglomerate viewed at Gale Crater. In the image at the right, we have a conglomerate viewed in the Atacama Desert of Earth. They look very, very similar. Here are some of the other sedimentary layers, and you can see in this we have fine-grained, fairly fissile rocks that are lithified, that are sedimentary, and they are dipping gently away from the mound at the center. If you look at the image at the right, you can clearly see stratigraphic divisions by looking at the frame. We have some low fissile beds near the bottom of this image, and then small mounds that don't show the same scale of bedding. They are clearly a different unit. So we can do stratigraphy from these images. We can recognize sedimentary features and sedimentary units and the stratigraphic contact between them by looking at frames from this rover. Here is an analysis of some of the mineralogy coming from the ChemIn instrument. In this frame, assuming it clicks, you can see that many of the minerals that are present in these rocks represent stuff that would come out of a basaltic igneous rock. We have plagioclase, we have olivine, we have pyroxenes such as pigeonite, augite, and statite. We have magnetite. Phases like that represent substantial fractions of some of these rocks. The rock at the left is a sandstone. The 2 or 3 rocks at the right are closer to where the rover landed, where it was on more clay-rich rocks. And so in this, you can also see that the rover down at the bottom has detected smectites, meaning loose, water-rich clay minerals are present at substantial abundances in those rocks, indicating a wet sedimentary component. That is a mudstone that we're looking at there. It still maintains some of the mineralogy of the original basaltic source rock, but in that case, some of that basaltic material has been converted to clay minerals. We see there are some other differences. This province also has some interesting minerals, some iron-bearing minerals, and in particular, in the sandstone at the left, we can see that there is sanidine present at a substantial abundance. That is one of the indications that this may have had an alkali basalt protolith. So, to finish up for Gale Crater, here is a basic model for how this crater was formed and how these sediments were formed. Start with our bowl-shaped crater and begin eroding with water material from both of the rims of the crater. That sediment will wash into the crater, creating deltas and lake deposits at the center of the crater that eventually filled up the crater almost completely, in fact, overtopped what we see from the crater today. Much of that material has since been eroded, creating this well that we see in the dashed line or at the bottom, where the rover landed on these delta and lake sediments and is gradually starting to climb its way up out of the crater towards the central peak, as you see in the topographic profile at the top of this frame. Now, finally, we don't have the rover here yet, but we will have one extra mapping project at a different site on Mars that is called Jezero Crater. A portion of this crater, not the whole thing, is seen here in an image that combines a CTX frame and some CRISM spectra overlay. The colors in this are indicating different minerals, which are some of the reasons why this will be the site for the upcoming Perseverance or Mars 2020 rover that will launch later this year. This site looks an awful lot like a delta. In fact, this site is thought to have been a Martian lake that was full for a substantial time. There are water inlets to this crater, and there seems to be an outlet for water, meaning that water was able to flow into this lake pond here and flow out in a regular hydrologic system. It has grown, as you see here, something that looks a lot like a traditional bird's foot delta shape, as you might see on Earth. And in this delta, there are spectral signatures of clay minerals again, of maybe basaltic protoliths, but there has also been recognition of carbonate minerals at this spot, and those are some of the reasons why this will be the target for the Mars 2020 rover, and why it has been mapped in great detail using orbital images and spectra, some of which you'll be able to sample in one of our exercises. So, if one is going to do some activities on Mars, there are a lot of things you can do. Geologic mapping from the orbital imagery, geologic mapping using the images collected at the surface. Stuff collected at the surface will allow you to recognize units, to do stratigraphy, to construct cross sections. We have the ability to analyze the texture of rocks based on hand lens images. We've analyzed the minerals and chemistry of rock. We have everything you need to do the types of facies analyses you might do on sedimentary rocks on Earth. Notably, however, there is one thing that you will not get in this area. Mars doesn't have the type of large-scale tectonic or structural features that we see on Earth. So we can practice many of the mapping skills that you'll want on Earth, but we can't have you go out and map thrust faults because there are very few of those features on Mars. Thank you, and I hope this is an interesting introduction to this area for you.